this video, we'll begin our study of sets in math. What is a set? Well, basically, a set is some kind of well-defined collection or group of items. In math, usually they're numbers, but they can also be other items as well. For instance, we might have a set of numbers, say 3, 4, and 5. And there are various ways I could describe this set. I could say this is the set of numbers, of natural numbers between 2 and 6, not included. To show that this is a set, I'm going to use the curly braces. And you've used those before when you wrote the solution set for perhaps an inequality or something else that has more than one solution. We often write our solution sets with the curly braces. Another element or another symbol that we use with sets is this kind of elongated E, and this is an element. So I could rewrite this and say that 3 is an element of the set 3, 4, 5. And that means is an element. Now, of course, if I do this and change this, 8 is not an element of the set 3, 4, 5. So that's just one of the symbols that we'll be using with sets. Haven't really done very much yet, but it's time to pause the video and work on checkpoint 1. Another symbol that you'll see when we're working with sets is the symbol for an empty set, which is a circle with a slash through it. This is the empty set. The empty set could also be written as a set of curly braces with nothing inside. These are equivalent. 0 is not the empty set. 0 could be an element in a set, but 0 written this way is just the number 0. If I do this, though, this is the set that contains the number 0. This is not the empty set. These things are not the same. Okay, so be very careful to distinguish between a set with 0 as an element, an empty set like this, and an empty set like this. These two are equivalent. This one is not. And of course, this is not a set at all. We say that sets are equal if they have all the same elements in them. So I could say that 5, 6, 7 is equal to 6, 5, 7, which is equal to 7, 5, 6. Okay, the order of the elements is not important, although it's nice to have them if they're numbers in numerical order, just so that, especially with larger sets, we can compare and make sure that they do indeed have all the same elements. Okay, but these are equal sets. Okay, I cannot say that this set is equal to this set because I don't have all the same elements. Okay, they have to be exactly the same elements although again, the order is not important. Okay. You've used in the past set builder notation. I'll go over it here very briefly. We say x such that x is greater than 4. That's a set builder notation that you might have used for the solution to an inequality. Okay, so when it has this vertical line here, that's read such that. And you will see that as we work through these examples. So let's work some examples. The first one is we want to write a roster for this set. I think you might all agree with me that this is kind of a cumbersome way to write this set. X such that x is a natural number less than 5. Recall that the natural numbers are also sometimes called the counting numbers. So when we count, we start with 1. So the set of natural numbers less than 5 could be written much more easily like this. Notice that 5 is not included in this set because it says less than 5. If we said less than or equal to, then we could include the 5. But for this description, this is our roster. This is our set builder notation. Let's look at another one. We'll see how good we are with geography. My set builder says x such that x is a state that borders Florida. So what are some states that border Florida? Well, my husband's from Florida, so I ought to know this. We could write, starting from the west, Alabama goes around the end of the panhandle there and up across part of the panhandle, and then right next to Alabama is, well, not Florida, Georgia. And Georgia and Florida share a border all the way out to the Atlantic Ocean. So this set of all the states that border Florida contains Alabama and Georgia. Pause the video now and work on checkpoint 2. There are some other symbols that we use when we talk about sets, and in particular when we compare one set to another. So we're going to start with this one, kind of a squash down C with a line, and this means is a subset of. So if I say A and B, this means A is a subset of B, which means that every element in set A is also in set B. We have a little different symbol. If I have that squash down C without the line, we say it's a proper subset. Subset. Cannot spell today. And what do I mean by a proper subset? In this case, A is a subset of B. If A and B were the same set, or equal sets, this would be true. When I take away the line, however, A has to be somewhat smaller than B. There has to be something in B that's not in A. So if I were to say, let's say, set A contained 1, 2, 3, and set B contained 1, 2, 3, 4, then it would be correct to say that A is a proper subset of B, because this element 4 is in B, but it's not in A. Now, if I were to add that 4 to my set A, now this is not true. Now I have to have the line here. This line is very similar to the line we have on inequalities. Okay, if I don't have the line, they can't be the same. And then the last symbol we have is this. And of course this means is not a subset. So let's go back to my set A, 1, 2, 3, and my set B. I'm going to make now 2, 3, 4. Now A is no longer a subset of B because 1 is in set A but not in set B. So it's not a subset. Okay, so those are 3 symbols that we use. A subset of, which can include the 2 sets being the same. Proper subset of does not include that condition, and not a subset. In this example, we're going to look at 3 situations and decide which one applies. M is a proper subset of N, or M is a subset of N. The next one is M is a proper subset of N, or M is not a subset of N. And my first situation is M is a set of all stocks that at least doubled in value over the course of a year. And N is the set of all stocks that at least tripled in value over the course of a year. My question is M a subset of N? Well, before a stock can triple in value, it's going to have to double in value. So I could say that everything that's in M is also in N. Could I use this? I could use this because it's reasonable to expect that not every stock that doubled is going to also triple within that time period of a year. So I would use this one. Let's look at another one. M is a set of all stocks priced $50 or higher on January 3rd, 2017. And N is a set of all stocks priced $50 or higher on January 2, 2018. So first trading day of the years 2017 and 2018. And it would be highly unlikely that anything that was $50 or higher in one year, that all of them would be $50 or higher the next year. It's just the nature of the stock market that prices go up and down. So for that situation, I would say that M is not a subset of N. There could easily be elements in M that were above $50 in 2017 and then in 2018 were not. We've got one more example to look at. M is a set of all stocks that increased in value over the course of a year. And N is a set of all stocks that increased in value by a penny or more as listed on the stock exchange over the course of a year? Well, when we list the price of stocks, it is rounded off to the nearest penny. So if it increased in value, it increased by at least a penny. So all of the ones that increased in value would be included in the ones that increased by at least a penny. So this would fit that third situation. Okay, let's look at some special conditions on subsets. It is correct to say that every set is a subset of itself. It is not correct to say that every set is a proper subset of itself, because these are the same. It's also correct to say that the empty set is a subset of any other set. Okay, the empty set is just a set that has no elements. That could be part of any set. So let's look at some sets with numbers. We want to decide if E is a subset of F. Is this true if E is 2, 4, 6, 8, and F is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Would it be correct to say that E is a subset of F? Well, 2, 4, 6, and 8 are all in here. So this is a yes. This E is a subset of this F. How about if E is the set of registered voters in Texas, and F is a set of adults 18 years and older? Well, the way the laws are set up in Texas, to be a registered voter, I have to be 18 years old or older. So this is a subset of this. Okay, one more. E is the set of diet soda drinks. And F is the set of diet soda drinks with NutraSweet. Okay, is E a subset of this set? And the answer is no, because not all diet sodas are sweetened with NutraSweet. Some of them have aspartame or some other kind of sweetener. So our answer here would be no. So pause the video now and work on checkpoint 3. Sometimes when we're working with a set, we want to know what all the subsets of that particular set are. So we'll use a method called a tree diagram to determine how many subsets there are for a particular set. And we're going to start with a very small set. And remember that, first of all, the empty set is always a subset of a set. And that any set that has at least one of these in it is also a subset. So for this one, we're going to say, does it contain 8? And the answer would be either yes or no. And then after we've answered that, let's put the contain 8 down here. Does the set contain 7? And my answer could be yes or no. So here it contains 8 and it contains 7. So that's considered a subset. If it contains 8 but does not contain 7, that's also a subset. If it does not contain 8, but it does contain 7, that would be a subset. If it doesn't have 8 or 7, it's the empty set and a subset. So for this set with 2 elements, I have 1, 2, 3, 4 subsets. Let's look at a slightly bigger set. Same process, just a little more to it. So we're going to start here with, does it contain A? Either yes it does, or no it doesn't. Then we're going to ask, does it contain B? And this would be yes or no. And then, of course, our third question is, does it contain C? If we've answered yes to all 3 questions, then it's A, B, and C. If we answered no on the last question, then it would be A and B. If we answered no on the second question, still might have C in it. So yes, no, yes would be A and C. Yes, no, no would be just A. And we can continue on. Here we'd have, this is my B question, yes or no. And then each of these would have to have a C question, yes and no, yes and no. So you see this gets a little cumbersome. But here we have no A, yes B, yes C. So that would be B, C. Then we have no A, yes B, no C. So that would be just B. No A, no B, but a C. So that would be set C. No A, no B, no C. Empty set. So I have 1, 2, 3, 4, 5, 6, 7, 8 sets. So from 2 elements that have 4 subsets to 3 elements, we have 8 subsets. Pause your video now and work on checkpoint 4. I'm sure you realized working on that last checkpoint that finding all the subsets of a particular set can be very wearisome and tedious. Sometimes it's just enough to know how many subsets there are. And so we can do that a lot quicker. The rule is for a set with n elements, there are 2 to the n power subsets. So that's our rule. So if I have this set looks like it might be eye colors. We've listed 4 different elements. So the number of subsets would be 2 to the 4th, which is 16. Okay, here's another set. X such that X is a month of the year. Okay, well there's 12 months in the year, so there would be 12 elements in that set. So there would be 2 to the 12th element, which is 4,096. Not 2 to the 12th elements, 2 to the 12 subsets. 4,096. And what about the empty set? How many subsets does the empty set have? And you might, before you say 0, let's use the rule 2 to the 0 power. There are 0 elements, but this is 1 subset because the empty set is a subset of every set. So pause your video now and work on checkpoint 5. One of the ways that we can show the relationship between sets is by using a diagram called a Venn diagram. A Venn diagram typically starts with a rectangle, and we call this rectangle the universal set, and frequently label it U. Other sets are depicted by circles and labeled with the set name. In this Venn diagram, we say that B is a subset of A because it's entirely inside A. Notice that the sizes of the circles are not meant to show the sizes of the sets. It's just the relationship between them. Pause the video now and work on checkpoint 6. Now we're going to take a look at some set operations that we use. I've got a Venn diagram here, very simple. This is the universal set, and this is set A. But another way that I could express that universal set is by saying A prime, because A prime is everything that's in the universal set, but not in set A. So it's kind of like the opposite of A. So A prime is everything that's not in A. Some texts use this symbol, and it means the same thing as this symbol. Those are equivalent. Okay, we call this the complement. These are the complements of set A. So let's look at what this is with some set rosters. I'm going to start with my universal set. And then I'm going to have set A. And set B. So if I wanted a complement, that would be everything that's up here, but not here. So it would end up being 2, 4, and 6. If I wanted B complement, I would leave out the 3, 4, and 6 and have 1, 2, 5, and 7. Okay, here's a kind of an interesting idea. Empty set complement. Well, everything that's not in the empty set is the universal set. And it just kind of stands to reason then that U complement, well, the universal set is everything. So if it's not in the universal set, that would be the empty set. Or we could write it that way. Pause your video now and work on checkpoint 7. Okay, time for some more symbols. If you see this between two sets, that stands for union. Pretty easy to remember. If you see this between two sets, that is the intersection. The union of two sets includes everything that is in either set, including things that might be in both sets. The intersection is only the elements that are in both sets. Think about the intersection of two streets. The intersection is the only part that is part of both streets. So let's look at some examples for union and intersection. So there's one set, 36 is what they gave us. And I want to intersect that with, so for intersection I only want things that are in both sets. So I see 15 is in both sets. And I can see that 25 is in both sets. But 9 is not over here, 36 is not over here. So this intersection is the set containing 15 and 25. Okay, let's look at another one. Set notation this time. X such that X is a teenager. And I want to intersect that with X such that X is a senior citizen. Okay, well, teenagers and senior citizens don't have an intersection. So this would be the empty set. If you're a teenager, you're not a senior citizen. Pause the video now and work on checkpoint 8. we're going to start with some new sets now and look at union. So here's my first set, union. And I think sometimes the easiest way to make sure that I get everything is to start with one set, and I'll start with the larger one. And I'll put 1 and 2 right next to each other because these are all whole numbers, so there's not going to be anything between 1 and 2, but between 2 and 5 there might be, so I'll leave some space there and write the 5, leave a little more space before I write the 9, and then the 14. Now I have places to put these pieces. The 1's already there, so I don't need that. But I do need the 3 and the 4. And I need the 8. And then after I'm done with that, I can kind of tidy it up a little bit and take out the spaces I didn't use. So that's a union. Let's look at another group. Types of dogs. I have the union with this other set of types of dogs. Okay, to make a union between these two, I see that Spaniels is repeated, so I'm going to take that out. And I'm also going to take out that U and this curly brace. So now I have one set that includes everything that was in both sets. I'll pause the video now and work on checkpoint 9. In this example, we'll look at how we can use sets to classify and analyze some different stocks. This table gives the 52-week high and low prices, the last price, and the change in price from the day before for 6 stocks on a recent day. Let the universal set U consist of the 6 stocks listed. Let A contain all stocks with a high price more than 50. We'll indicate these by circling those high prices. B is all stocks with a last price between $25 and $80, shown with the green circles. And C will be all stocks with a negative change value, indicated by the purple circles. Now we want to find the results of the given set operations. The first one is B complement. So we want the stocks where we did not draw a green circle. This would be the set of Ford, IBM, Netflix, and Procter & Gamble. The next set we want to look at is A intersect C. So these are stocks where we circled both the orange and the purple. So this would be First Solar, IBM, and Verizon. A union B would be all the stocks that had either an orange circle or a green circle, which is everything except Ford. So First Solar, IBM, Netflix, Procter & Gamble, and Verizon. Pause the video now and work on checkpoint 10.